Hello, we are starting on a new topic, RTL combinational components. And what is RTL? And combinational components, we have already uh, been talking about combinational components, combinational circuits, components or circuits that do not have any memory. Okay, actually, so far we don't know otherwise. Everything we have seen so far, gates, transistors, putting gates together, putting transistors together to making gates and all of those are combinational. Okay, meaning that they have no memory whatsoever. But then what we do now is go transistor, gate. Now we go one level up and we say what is beyond gates. And why do we need to go beyond gates? What we have done so far is we have shown you gate level design. Uh, we have shown you something like, for example, an adder overflow detector. We have shown you Boolean expressions that you can write. They can be very complex. And we have also shown you how to minimize them. Okay, and so far this is what we have done. But then what is beyond this is can we live with the methods so far presented so far? Are these enough for large combinational circuits, for large digital systems? So I'm going to look at RTL, which is one level beyond gate level, and talk a little bit about the properties of RTL. The reason I'm doing this now is to be able to justify why we need to go up one level from gates to RTL. And then once we are able to see that, then we go say, well, let's do some standard components in RTL. And also let's talk about the very long descriptions corresponding to these components. So let's get it started. So what is RTL and why RTL? Let's look at a simple circuit, this, and try to do this using what we already know. What do we already know? Well, we know that we can take many inputs and we can build Carnot maps, and if worse comes to worse, we can even do 6 variable Carnot maps, and so that's good. We can build circuits. And if, for example, we have a need for building a 3-bit adder, A2, A1, A0, B2, B1, B0, the output will be some 3, some 2, some 1, some 0, and then carry out. And then we can start with 0, 0, 0, 0, 0, 0, and then just write down the results. And then we have what, 1, 2, 3, 4 outputs, and then these 4 outputs, each of them requiring a 6 variable Carnot map. Wait a minute, we have done 2, that was pretty good. 3, that was good. 4 variable Carnot map. Okay, that was acceptable, doable. But 5 variable was doable. 6 variable, we just showed 6 variable, but then we said nobody touches that, nobody gets close to that. So how do I go about designing something like this if Carnot map is not going to do the job? And what I'm looking at here is something even worse. I'm telling you the A input is a 2's complement number, 8-bit number, and I want to build a circuit that comes up with the absolute value of this circuit. Okay, well, right here, I said 6 variable map is impossible. It's not impossible, but then it's bad. Uh, but then for the absolute value circuit, I'm talking about 8 variable maps. And even more than the adder circuit here, I need eight variable maps. So that's not the way. That's really not the way to go about this. An example is this is a negative number because a is 1 on the left hand side, the sign bit of it is 1, and therefore the absolute value becomes what is on the right. Remember how to go from from let's say negative 2's complement number to positive, or the other way around, positive to negative. The way it works is you start from the right hand side, repeat this as is, and then from that point on, after the very first one, everything else complements, and therefore the complement of it becomes what is here. On the other hand, another way of doing this same 2's complement conversion is to say, well, let's do this. Let's complement this. Okay. Complementing becomes 0, 1, 0, 0, 1, 1, 0, 1. Okay. And then add a 1 to it. So it becomes 0, 1, 1, 1, 0, 0, 1, 0. So you can do either, right? In any case, what is on the left, then you add a 1 to it, and then complementing add a 1 to it, you get what is on the right, which is the absolute value of the number on the left, on A. And but I'm asking you to build a circuit to do this, and then you say, well, eight variable Carnot maps, that's not possible. So how do you go about this? And obviously one way would be to list all the values, all the 8, that means 256 values, and then for every single number, write the outputs, and then come up with the truth tables, Carnot maps, and all that. And this is it, right? 8 variable Carnot maps. That's impossible. You cannot do that, okay? In a way, maybe it's not worth doing this. For a circuit like this, for a simple circuit like this, I should have better ways of doing it. But look at what I just said. I said that if you take the input, look at the sign bit. If the sign bit is positive, the number is as is. And if the sign bit is negative, that means it's a 1, then you complement and add a 1 to it. What if I just turn whatever I said into hardware? Look at the input. Okay, look at the leftmost bit of the input. If it's a 0, don't touch it. Let it go through. Okay, if it's a 1, then complement the whole thing, add a 1 to it. So I kind of changed the problem into 3 smaller problems. I said, look at the leftmost bit of A, this one, sign bit. Okay? If it's 0, let it go through as is. If it's 1, then don't let that go through, let something else go through. So let's do this. Let's come up with a multiplexer. Put all of A on the upper input. These are 8 2-to-1 multiplexers. And then let's take the sign bit of A, which is bit number 7. Okay. If this is 0, what happens on the output is just A. If it is 1, then don't let that go through. Instead, If that is 1, take all of A, okay? Complement the entire thing, and add a 1 to it, and then let that go through. Okay? So what happened here? Well, I turned my problem into 3 smaller problems. One problem is the multiplexer here. Let's build a small multiplexer, a 2 to 1 multiplexer. Small means small number of inputs, multiplex to the outputs. One circuit is complementing 8 bits of A. Well, that's easy. Just put 8 inverters in parallel. And then the third problem I'm talking about is once you complement, add a 1 to it. I call that an incrementer. So see how I did this absolute value circuit. The way I did it was I said that I'm not going to look at the logic. Okay, I'm not going to look at the gate level logic. I'm going to look at it from a more abstract point of view. I will look at the algorithm that I would use for doing this. And the algorithm tells me, look at the sign bit. The sign bit selects either A or A complemented plus 1. And then just these wordings I turned into components. Selecting is a multiplexing. Complementing, obviously, is using inverters. And then plus 1, I said, well, plus 1 shouldn't be that difficult. Okay? So I turned my more complex problem into some subcomponents. And then I do this. I say, okay, let's go in my bag of combinational components. Do I have a multiplexer? I look at, yes, I do have a multiplexer. Do I have an array of parallel inverters? Of course I do. Do I have an incrementer? Yes, I do. So what I do is I don't deal with gates anymore. I deal with these upper level components. Okay? I deal with these upper level components. Another example, maybe you want to design a circuit that would take the maximum of A and B and put it on the output. Okay? Again, I don't want to deal with gates. I want to deal with upper level components. I say, this is A, this is B, okay? And then I need a multiplexer. 0, 1. That's an 8-bit or octal 2 to 1 multiplexer. And then I say, I use a comparator. Okay. If A is less than B, no. If A is greater than B, I let A go through to the output. If A is less than B, I let B go to the output. This is a maximum finder circuit. Look, if I wanted to do this using Carnot maps, I had to have 8 16 variable Carnot maps. That's impossible. But by looking at the high level description of this, I said, I need a comparator and a multiplexer. And then I go look in my bag. Do I have a comparator in my bag? Oh, maybe I do have a comparator, but it's only a 4-bit comparator. Can I cascade that to make it an 8-bit comparator? Yes, I can cascade it to make it an 8-bit comparator. So let's take two 4-bit comparators, put them together, make an 8-bit comparator. And then how about the multiplexer? Well, the multiplexer, maybe I have a 2 to 1, maybe I have again a quad 2 to 1 multiplexer. I put two of them together, I have this, and that's all this. So, or maybe not. Maybe I have a multiplexer that is octal 2 to 1 multiplexer, and a comparator that is finding the greater of two 8-bit numbers, or I'm sorry, that is comparing two 8-bit numbers and coming up with the greater output. Okay, and if this is the case, then my problem is solved. I just put the comparator there and the multiplexer, and I'm done with this. Now the question is, what are these components? Okay, what are these components that I have? Well, I already showed you two small examples, both of them using a multiplexer. Okay, so multiplexer is it. I need the multiplexer. It comes handy in a lot of situations. An adder, yes, an adder is a good one. How about the subtractor? Yeah, subtractor. You want to compare something with something, you can subtract them and see if the result is 0 or not, or negative or not. So that's something. Comparator, just for comparing, yes, that's a good thing. Okay. Incrementer, yeah, incrementer can be extracted from adder. So let's also have an incrementer. An array of gates, yeah, array of gates is easy because in one case maybe I need to select either my, let's say data 3, data 2, data 1, data 0, or I want to have 0 selected instead. Okay, so if I put a 1 here, D goes to the output. If I have a 0 here, 0 goes to the output. So an array of gates comes handy a lot of times. What are these components? I refer to them as RT level components. What are they? Is it a decoder? Is a multiplexer? Is a adder? Is a comparator? Is a circuit that does sometimes add, sometimes subtract? It is a circuit that does some logical operation and some arithmetic operations. I call that an ALU, arithmetic logic unit, and a few other ones. And this is the topic of discussion here. Okay, let me talk about RT level, and then we come back to this. Before doing that, let's do the promise that we had and at least do the absolute value circuit. The absolute value circuit works like this. I take W, okay, complement all the bits. Complementing goes into an incrementer, but then I have to design the incrementer, okay? It is in my bag, but then I have to design it. At least I have to show the design to you once, okay? I design that, and then I have the multiplexer, and then I show you the multiplexer design, and then whatever we design is we design it, understand it, and then write the very long description of it in various forms, put the component in the bag. Anytime you want, just grab it and put it there for whatever application requires it. So that's why you do RTL, because you are tired of doing gates. The same way when we went from transistors to gates, remember, from transistors to gates, we said, well, I can do a lot of good designs with transistors. Actually, when I was taking logic design, gates were good. Gates were high-level components. And then people were putting transistors together to build gates. But then, gates become more complex. Functions become more complex. And then you say, well, I cannot put gates together forever. So you go from transistor level to gate level. You exercise that, you learn that, and then you say, well, let's go one level higher. Let's go instead of gate level, let's go to RTL or register transfer level. And then learn the components at that level. And then put those components together for your designs. I just showed you two very, very simple RT level designs, but RT level designs are not as simple. So we are saying people in the 70s used to do transistors. Really, they were doing transistors. In the 80s, they were doing gates. Okay? And then RT level started late 80s and then matured in early 90s. Today, nobody designs at the gate level unless you have some specific function that you want to optimize for some little area on the chip. Today's design are all at the RT level. Okay? But then, RT level is reaching or has reached its limits as well. Functions have become far more complex than what RT level can handle. Okay? So when you have a hardware you are designing that grabs an image from the front of your vehicle, and that image has to be analyzed, it has to be filtered, the color has to be removed, and then you have to detect an edge, you have to detect street lines, you have to detect a car in front of you or a pedestrian in front of you. These are not simple components that I can design at the RT level. So what do? Once I design certain RT level components, okay, like a filter, right? Then I say, well, now let's go to system level. And then I remember I had a bag of little RT level components. Then I have RTL subsystems, like a filter, like a floating point multiplier. I put those in my other bag. And then when I'm designing at the system level, I look inside my RTL subcomponents. Those are filters, trigonometric functions. Those are floating point multipliers, or even a little CPU. CPUs are in my right-hand side bag that RTL subcomponents are in there. Every once in a while, though, the same way, look at the inverter example that I showed you here. The same way, I go into gate level and put a few gates together in the case of inverter. Every once in a while, when I'm doing system level, even though I have RTL components, RTL subsystems, but then every once in a while, I say, well, I really need a multiplexer, even though I'm dealing with this filter and the floating point multiplier and all that. So I have another bag that has these little RTL components, and I grab those as well and put systems together. But that's not our concern here. Our concern is what I'm showing here. Okay? My concern is this. And look. It shows certain busing structures, wires connected together, components like an ALU connected together with maybe a register, maybe a counter, maybe a comparator and things. Okay, this is what I'll be dealing with. What is that thing? What is RTL? This is just a zoom of what that little RTL that I was showing. RTL has adders, multiplexers, registers that are sequential components, which I'm not talking about here. It has bus structures or multiplexing. These are multiplexings. comparators. Okay? And then RTL has two parts. RTL on one side is a part where these operations are done, adding, comparing, and all of these are done. And on the other side of RTL is a control unit that tells these RTL components what to do, or when to compare, when to add, and so on. Okay? So, a combinational component of RTL is ALU. How are these put together? These are put together with also sequential components. Once again, I'm not concerned with sequential components yet. I will get to that before the end of the course. Okay? But there's something else that we need to say. I have sequential components. I have combinational components. I put them together. Okay? And then come up with a data path. The data path has combinational and sequential components put together. The data path only has the operations. The operations is adding, subtracting, storing data, multiplexing data, and all of that. And then there is somebody else that controls the operations in the data path. That somebody else is the controller or the sequencer. That somebody else decides when my ALU is going to add. When my program counter, for example, my register, is going to store data or is going to count. Okay, that too we will be doing in this course. So what's coming is this. I will cover combinational components like what I said, the ALU and the comparator and all that. Okay, then we say, well, this is not enough. I have to talk about memory elements. Then I talk about sequential components. Once I'm done with those, then I say, well, I have to also design something like this timer sitting here saying that I have to control the operations on the, in what I'm calling the data path. So we have to design that. This is RTL. The RTL is controlling ALU, is controlling the program counter, the registers, is controlling everything that happens here. And then once we cover sequential circuits, we will also talk about controllers. Okay? So, this is a big picture. This is a general overview. Now let's focus on, let's say, for example, what I said, things like the ALU. Things like the multiplexing that is done here, which I'm calling busing. Okay? Things that go inside my data path. Things that decide what are the operations to be done. Okay? So, an RT level circuit has a controller. That's a sequencer, that's a timer, and a data path. The data path has sequential components and combinational components. Our focus here now is on combinational components that go within the data path. Something like that absolute value circuit that I did. Something like that maximum finder circuit that I did. Now, those are very simple. They didn't have any memory elements. They didn't have any sequencer to deal with the doing when things. Nevertheless, they were the data path of a very, very simple RTL. So these are the components in the data path, or the components that we'll be dealing with, the components that we will be analyzing, designing, and putting in our bag. Okay, let's start with that.